So we have a very simple way of designing our memory management unit. It's a table, and you index the table using the virtual page number, and what comes out of the table is the physical address. Right? So it's just a table of physical addresses. How many entries are there in the page table? I need one entry for every virtual page. Some of the entries have a valid, you can see down here, I have this so-called R bit, the resident bit. Okay. If the resident bit is 1, that means that if I'm asking for virtual page 0, I actually have a corresponding physical page. I check the R bit in the 0th entry of my page map, and I say, aha! And then I just use whatever number appears here as the high order bits of the physical address. The page offset just flows right through. Everybody sort of happy with that? Very, very naive, simple implementation. Okay, but depending on how many virtual pages I have, the page map itself may be quite large, and we'll talk more about that in a second. And here, by the way, you can see the dirty bit. We've allocated room for the dirty bit. So typically a page map has these two control bits, a dirty bit and a resident bit, and then the physical page numbers. And you can see whenever the R bit is 0, that means for that particular virtual page, we do not have a corresponding physical page, and that'll generate on the hardware what's called a page fault exception. Okay, so that's the page map. You notice there's a lot of similarities between this and the cache, right? Mostly it's a matter of, first of all, that we tend to, the chunks of storage we're dealing with are thousands of bytes instead of maybe just a small block of words. So we're moving, in these big pages in and out of disk. In fact, we may actually move multiples of pages in and out of disk for much the same reason as we did big blocks of words in our cache, because the disk has lousy latency but reasonably good throughput once you've got the head in the right position. So maybe we should bring a bunch of pages in when we're doing it. So we have large pages in RAM, but there's a lot of similarities between these two schemes. And you can almost think of main memory now as being a cache for what's on disk. And that analogy will stand you in good stead so long as you remember that the miss time is huge, much, much larger than it is when we missed going from the cache to physical memory. Okay, so this is sort of the hardware view, this notion of this hardware page map. Think of it as just a big piece of SRAM that has this number of bits in each memory location, and it has enough memory locations to provide a one-word entry for each virtual page. So one entry per virtual page. And we have the R bit that tells us whether the mapping is valid or not. So 1 means that I can produce a physical page number and complete the access to main memory. And the 0 means that I'm sorry, that's currently an invalid address. So I don't have any, doesn't live in main memory. So either I have to get it from disk, or if it hasn't been allocated to you at all, I'll bitch and either maybe I'll allocate it to you automatically in the case of a stack access, or maybe I'll simply give you a nice blue screen and tell you, sorry, just reboot your machine. Okay, and the dirty bit is remembering that if we change any of these pages, when we replace it as part of our replacement strategy, as we bring more pages in, we actually will end up having to rewrite it to disk so that the copy of the pages on disk will always eventually be correct. I mean, we won't lose any information that's been written to a page. Now the 6.3 view, you can think of this as really a couple of subroutines whose job it is, their translation. Their job is to translate virtual to physical addresses. So I bring in the address segmented as a virtual page number and a page offset. And what this subroutine's job is its job is to produce a physical address back. So this is like a procedure call that says, here's a virtual address organized as a page number and offset. Please give me back a physical address that I can send to memory. And then so this is the access into the page table, checking the resident bit, and if it's 0, producing a page fault, otherwise using the physical page number information and concatenating it with the page offset to form the physical address. Page fault is sort of this, is handled separately down here. And typically, this part here, this virtual to physical address translation, is done in hardware, so it's fast. And then page faults really are a synchronous exception to the running of your program, and then we go to some sort of operating system routine whose job it is to figure out the more complicated process of finding the page on disk, figuring out what page we have to get rid of, and if so, write it out, so forth and so on. And if you actually look at this code, you'll see that what that code is doing. It's selecting the least recently used page. If the dirty bit is 1, it writes it back out onto disk. At that point, the resident bit for the LRU page is we picked a, sorry, so let's see if I can be clear. I is the virtual page number of the least recently used page. So we're looking in the page table, which is of course indexed by virtual page number. And what we're doing is we're sort of cleaning up the database for that particular virtual page. If it's dirty, we write it out. And after we've written it out, we say that page is no longer resident because that's the one I'm moving out. Then I go off and I'm going to use that. I'm going to go find out the physical page number that it used to live in, and that will become the new home of the page that I really wanted. Right, so when you saw me swap out the one down here, this code, this procedure that you see here is really doing all the bookkeeping associated with updating the MMU state that corresponds to that swap. So it's just something you can sort of puzzle through a bit. Any comments or questions about that? Yes? Crash. Yes. So according to this balance, if the R bit is 0, you cause a fault. The response to the fault, in other words, what the operating system will do, that depends on a bunch of bookkeeping that it's doing in software about whether that address has been allocated to you or ought to be allocated to you, or whether it's just an illegal address. And that's just part of the bookkeeping associated with the operating system. And we'll be spending some time talking about that level of bookkeeping in the next couple of lectures.